Welcome back, Honors Chem Stars. It's time to go over Chapter 12 homework, page 9. And we're going to be looking at stoichiometry calculations involving aqueous solutions. Remember, M equals N over L. That means the molarity, the concentration, is equal to the number of moles over the volume in liters. Helpful conversion factors, if you've forgotten, 1,000 milliliters equals 1 liter. And we are infinitely sure about that. That conversion right there has infinite sig figs. Okay, let's look at number 1. A useful application of oxalic acid is the removal of rust, Fe2O3, or iron 3 oxide, from the bathtub rings according to this reaction. So it was already balanced for you. We have rust, or iron 3 oxide, plus oxalic acid yields this aqueous product, iron 3 oxalate, plus 3 water, plus 6 free H+ ions. You're going to calculate the number of grams of rust that can be removed by 500 mils of a 0.1 molar solution of oxalic acid. This is going to be a BCA table problem, but we've got to do a little bit of work first, because remember, only moles ever go into the BCA table. So we need to find the number of grams of rust. We'll be solving for the moles using the BCA table, and then we'll convert moles to grams using the molar mass. And we've got to convert our milliliters to liters. That's really easy. So let's go 1, 2, 3. So 500 mils, that's actually 0.5 liters. I did that right here. They gave us the volume and they gave us the concentration. We have to solve for number of moles here. So the number of moles is molarity times the volume. So molarity is 0.1. Volume is 0.5. So how many moles of oxalic acid do we have? Well, I hope you can do that one in your head. If you can't, we're going to take 0.1 times 0.5, and look at that. We get 0.05. So for our oxalic acid, we have 0.05. Technically for Sig Figs, we need 2 more trailing zeros, and that's going to be moles of our oxalic acid. Okay. So here's how we should be filling that in. So we are taking our 0.0500 moles of oxalic acid, and then we want to find out exactly how much of the rust we can remove. So how much of that oxalic acid will be using up? We'll be using up all of it. There'll be none left. So during the reaction, we're going to use up all of that oxalic acid. They don't even ask us anything about this part of the BCA table, but in general terms, we can say we start with no products, we create some positive amount of products, end up with some positive moles, but it doesn't even matter right now. Okay, so how much of this, oh, Pickles is barking, hold on. Okay, so how much rust can we remove? Well, we'll exactly use up each, so afterwards we'll say that the rust is 0. Now, it might not actually be 0 left in your bathtub, but they're going to be exactly used up. So how much rust can we remove during the change? We're going to be removing 0.05, I'm not going to write the zeros afterwards because I don't have enough room, times the ratio of the oxalic acid to the rust. So this is the amount that we're removing. Okay, and this is what the actual answer really is. But to make the BCA table nice, so we're going to take that 0.05 times 1 over 6. So times 1, or divide by 6 here, 0.00833. So we're going to be starting with 0.0833. So what we're just saying is that that's how much rust we're removing. Okay, but is that the final answer they want? No, they want grams of rust. So we got to take this number. So we have 0.0833 moles of rust, and we want to get rid of our moles, and we want to go to grams. So we have to go to our periodic table. We need to find iron 3 oxide. Look at that, right up here, 159.7 grams per mole. So 159.7 grams per mole. So times the molar mass, we get a mass of 1.3308. 1.3308 grams. Last thing is we want to check for Sig Figs. Okay, here we had 4 Sig Figs. Here we had 1, 2, 3 Sig Figs. So we're going to go to 3. 1, 2, 3. Look to the right. So it's going to be 1.33 grams of rust. That's how much we can remove just using that much from your bathtub. Okay, problem 2. Oh, Pickles is grumpy. He's growling if you can hear him. Okay, problem 2 says, how many milliliters of a 0.106 molar copper 2 nitrate solution is required to form 6.52 grams of solid copper 2 hydroxide? Here's the equation. You had to balance it yourself. I just put hydroxide in parentheses here. That way you can see how it balances easier. And this is going to be another BCA table problem. So let's just kind of look at the skeleton of the problem here. So what do we know? We know that we're going to be starting with some moles of copper nitrate. We're going to figure that out from our molarity calculations. And they want to know how much. Okay, so first things first, we got to put some moles into this BCA table. This one we're going to kind of work backwards from the product. We know that right here, we're ending up with 6.52 grams of solid copper 2 hydroxide, but we need to know how many moles that is in the periodic, or in the BCA table. So to do that, we're going to go to the periodic table, copper 2 hydroxide, so CuOH2, there's 1 copper atom, then there's 2 hydroxides. We add all that up, we get 97.57 grams per moles. Okay, so use your calculator. We need to take 6.52 grams, divide by the molar mass, 97.57, and we get how many moles? 0.0668. So 0.0668. Now, how many sig figs do we need? Oh, we need 3 at the end. We should throw another sig fig on there, 6682, just so we can be specific here. So this is what we're working backwards from, 0.06682. Okay, this is the final moles. So how did we get that? We got that from some coefficient times the ratio of the copper 1 hydroxide to the thing we want to know about, the copper nitrate. Well, look at that. It's 1 to 1. That's nice. So 0 plus some coefficient, some number times 1 over 1 is 0.0668. So what is that question mark? What is that question mark number? Well, it's that same number. Anything times 1 is itself. So how many moles of copper 2 nitrate did we use up? We started with 0.06682. We used up all 0.06682. There was none left at the end. And then if you work backwards, or actually work forwards to check your work, you take this number, 0.06682. That's our question mark here. Times 1, do you get 0.06682? Yep, it works. But this is our number of moles. Now, I know it was 0 at the end, but we're taking that 0.06682, and that's my moles of copper 2 nitrate. And we need to convert that back to a volume. Okay, so here's what we do know. We know that the concentration is 0.106 molar, and we know that M is N over L. Rearrange and solve, L is N over M. We just solved for N, our number of moles, so 0.06682, and then divide it by the concentration. So take our number, divide it by 0.106, and here's our volume in liters, 0.6304. So 0.6304 liters. But here's the problem. They don't want liters, they want milliliters. So what's the last thing we have to do? Oh, let's try and figure out why our smart screen is smarter than I am. We need to take it times 1,000 to get to milliliters times 1,000. And we get 630.41. Now, we want how many sig figs in that one? We want 3, so 630 point. 1, 2, there's your third sig fig. Look to the right. Will the 4 round that up? No. And so we have to say 630 milliliters. Now, the way I wrote that, only 2 sig figs. Make sure you put that point at the end. That means decimals present. Count from the Pacific, 1, 2, 3. That decimal makes the 0 significant. Now, you don't have to fill in the rest of the BCA table because it didn't ask you to. Last problem on this page. Okay. If 3 grams of copper wire is placed in a 150 milliliter solution of 0.2 molar silver nitrate, we actually did this back at the beginning of chapter 8. Remember in the chem lab, I took the copper coil and I put it in the solution and it grew these really pretty feathery silver crystals? Same reaction. So how much silver is produced? Hint, this is a limiting reactant problem. Both reactants are given, so one of them will run out first. You need to decide which one of that will run out. So let's look back to this problem. So we want to start with a BCA table. Let me extend my page a little bit. We want to start with a BCA table, and let's say what we know. We know before the reaction starts, I've got some number of moles of copper and silver nitrate, my reactants there. Before the reaction starts, I have no products. I'm creating some positive product, and the one they care about is how much silver is made. So out of my BCA table, I'm going to get moles of silver. Then I'm going to have to multiply by the molar mass of silver, which you get from the periodic table right here, 107.87. And then that will be my grams of silver. This is the final answer. But I've got to do some work to get there because my input moles are missing. Okay, so I need to get moles of copper first. We'll just work left to right. So if 3 grams of copper, I'm going to take 3 grams and divide by copper's molar mass from the periodic table. So you find copper, molar mass is 63.55. I'm going to divide that. So 3 divide by 63.55. I have 0.0472 moles of copper. So I've got 0.0472. I'm just going to put a point here, 0.0472. I don't know what I'm running out of yet. I have to figure out how much of the copper nitrate I have. Okay, so the copper nitrate we've got to do a little bit more work with. So we have 150 mils. Remember, quick trick, 1, 2, 3, that's 0.150 liters. And they told us the concentration. We need to find out N number of moles right here. So N is M times L. Molarity is 0.20 molar. L is 0.150 liters. So we're going to take our 0.2 times 0.15, and we're going to get 0.03. So 0.03 moles of silver nitrate. We're going to plop that over here to the BCA table, 0.03. Now, which one of these do you think will run out of first? Okay, what do we have more of? We've got more of this one. And when you look at it, look at the ratio. We actually need more silver nitrate than we need copper. So we need twice as much silver nitrate. If this was limiting, we'd need like 0.94. Do we have 0.94 or 0.094? No, we got 0.03. This one we're going to bet right now is limiting reactant. Now, if we chose wrong, how will we know? We will get a negative answer right here. So let's assume that this is my limiting reactant. It's going to go to 0. Think back to chapter 9. Now, look, this is the test here. See if we're right. So how much copper will be left over? We need to solve this before we can move on. I'm going to be using up that 0.03 times the mole ratio. So we want to cancel out that silver nitrate and get what is left for the copper. So we've got to figure out what this number is. Okay, so 0.03 divided by 2, 0.015. So this number right here is actually 0.015. Let's do some fast math here. Can we subtract those numbers? You betcha. So 0.0472 minus 0.015. How much is left over? 0.0322. And that's going to be excess. Remember, if that number had been negative, we would have chosen the wrong limiting reactant. To go back and redo it. Okay, so this means we've chosen correctly. Now we can go ahead and figure out how much silver nitrate, or how much silver we've created from the silver nitrate. So we're going to be creating that coefficient, 0.03 times the ratio. The unknown silver's coefficient is 2. The known silver nitrate is 1. So what's going to happen here? We're going to double it. So 0.03 times 2 over 1, 0.06. So 0.06, and that's how many moles of silver we've created. But the problem wants to know how much silver. Well, I guess we could leave it as moles, but we want to know grams of silver. Then we can Google the price of raw silver and figure out how much you can make taking it into like a jewelry store. Okay, so 0.06 times 107.87 times 107.87, and that's 6.4722. 6.4722 grams of silver. Last part, look for Sig Figs. 1, 2, 3 Sig Figs, 1, 2, 3 Sig Figs, 1, 2 Sig Figs. Okay, so 1, 2, my least number of sig figs, that's my precision there. Look to the right, that will round it up. So my final answer is actually 6.5 grams of silver. If you want to know how much that's worth, you can just Google the going price for silver in grams and figure that out. Okay, that's the end of page 9. I'll see you next time, guys. Remember, don't wait to be great.